Hello everyone, this is Ravan from IEEE Senior Core.
And this is Rohit Paramesh.
Yes, welcome to the session on computer vision where we will be covering about everything about computer vision from A to Z. So computer vision is a rapidly evolving field of artificial intelligence that involves enabling machines to interpret and understand visual information around the world. In this session, we will be exploring the fundamentals of computer vision, including image processing and machine learning techniques. We'll also have some fascinating live demonstrations, which you will be, which makes you to drive through your interest. And whether you are new to computer vision or looking to deepen your knowledge, this session is for you. So get ready, buckle up, and then let's dive into the fascinating world of computer vision. So, computer vision is an interdisciplinary field of study that focuses on enabling computers to interpret and analyze digital images and videos from the world around us. It aims us to replicate human visual system to enable machines to perceive, understand, and interpret visual information from the world and make decisions based on the given information. So computer vision techniques are used in wide range of applications, including robotics, surveillance systems, medical imaging, autonomous vehicles, and so on. The list goes on. The main goal of computer vision is to develop algorithms and models to detect, recognize, classify, and then track objects, events in visual data to extract useful information and insights from the data. So now let's start seeing about the brief history of computer vision, which is very important to get started with computer vision actually. So here is the timeline. Okay, so the timeline starts from 1970s. So in 1970s, we saw the people and researchers saw the development of early computer vision systems that could recognize simple geometric shapes and then perform edge detection. Researchers also started to begin exploring the use of artificial intelligence and machine learning for the image recognition in the year of 1970s. And then next comes the year 1980s, where the first commercial image recognition systems were developed. And then they started to apply it on industries such as automotive and manufacturing industries. And researchers also made significant progress in stereo vision and then optical flow motion analysis and these kind of things where they started to work on in the year 1970s. So in 1990s, the computer vision engineers and researchers started to focus on object recognition and then face recognition, feature extraction, and then within these 10 years, we started to see the we started to develop many applications in computer vision using computer visions, and then we started to explore the use of neural networks in image recognition as well. And in the year 2000s, the year 2000 is called the era of internet and then digital camera side. So we started to get more information from the internet, and we started to make even more better analysis and then object detection, classification, segmentation, and it goes on. And in the year 2010s, we started to we started to utilize the main concept, which is called deep learning, which consists of neural networks and other architectures, highly complicated architectures, which are prone to give high accuracy, and then high accuracy in image recognition systems. And then we started to use in various fields like self-driving cars and then medical imaging and facial recognition, etc., with a great amount of accuracy. So this is about the brief history of computer vision. And then we are going to start about importance of computer vision in real world. Okay, so computer vision is actually an essential technology with numerous practical applications. So here are some of the reasons why computer vision is important. So the first one is automation. So computer vision enables machines to perform tasks that would otherwise require human intervention, you know, like detecting defects in manufacturing, monitoring the traffic, and the list goes on. Okay, so as I given in the picture, okay, here we can see a factory which manufactures bottles. So we can, the computer vision systems are able to detect the like the broken bottle in the given set of bottles, right? So here the the machine starts to automate the things using computer vision. So the real-time example of these kind of applications are used in BMW manufacturing centers. Okay, so BMW uses computer vision to inspect the paintwork of its own vehicles, during the manufacturing process. So the system can actually detect defects such as scratches, bubbles, dents on the surface of the car, and then it ensures that the final product is of high quality. There is the use of computer vision in automation. So next application is in healthcare. So like in healthcare, computer vision plays a critical role in medical imaging, which includes X-rays and then CT scans, MRI scans, and so on. It basically helps the doctor to detect and diagnose, plan surgeries, and monitor patients easily. So the real-time application here is in IBM Watson Health, so which is developed by IBM basically. So IBM Watson Health uses computer vision to analyze medical images and then data to improve patient care. So the system can also help in identifying patterns and anomalies in patient data, and then enabling physicians to make more informed diagnosis and then treatment decisions. So this is the real-time application of computer vision in healthcare industry. And then the importance of computer vision in autonomous systems. So computer vision is essential for developing autonomous systems such as self-driving cars, that Tesla cars, and then drones, robots, etc. And it enables these systems to perceive and interact with the environment, avoid obstacles, and make decisions based on the visual data and the environment. So the real-time application, as everyone knows, it's a Tesla car, which is a self-driving car. Okay, so these Tesla cars uses computer vision for its autopilot mode. Okay, which provides advanced driving assistant features such as lane keeping, adaptive cruise control, and then self-parking features. And then these systems, like this system uses a combination of cameras, radars, sensors, etc., like many other sensors to detect objects and hazards on the road. So this slide is for you guys. Let us know any other applications which you guys know regarding the computer vision. Please let me know in the chat. Any other application, guys?
Come on, guys, let's see some activity in the comment section. All right, so moving on, let's start with image processing. Yeah. So before we understand in depth in with how computer vision exactly works, we need to understand what image processing is because image processing forms the basis behind computer vision. All right. So let's start with the bare basic image fundamentals. So ideally, we have two types of images. One's a vector and the other is a raster. All right. So by definition, raster images are essentially defined as a grid of pixels where each pixel is represented by a color value. And most of the time, you would probably know them as bitmap images. All right. Um, on the other hand, vector images are essentially geometric primitives. What that exactly means is that instead of assigning a color values, to each pixel, we just define it to be shapes. So that way it makes things easier for us when we're processing the image. So let's talk about how vectors and rasters are different in terms of scaling. Yeah, so one of the main difference between vectors and rasters when it comes to the scaling of images is that when you zoom in, when you try to increase the size of the image, Raster images can sometimes, lose quality when they are scaled up. But vectors usually don't have that problem because essentially they're just commands of mathematical primitives. So the more you zoom in, the computer adjusts the mathematical primitives so that the quality of the picture doesn't essentially change no matter how you scale it up or scale it down, and it's constantly recalculated and redrawn at its new size. Now, in terms of editing, they are very different again. Raster images are edited by manipulating the individual pixels because they are obviously individual pixel values. And vector images, on the other hand, are edited by manipulating the geometric primitives itself. So, editing a vector may be faster and more precise for complex images, but it's kind of difficult when it comes to rasters because it ends up being a very time consuming and a more complex procedure. Yeah. So in terms of file sizes, raster images can have larger file sizes, especially for higher resolution images, because each pixel in the raster has to be individually sorted. And in terms of vector images, they can have really small sizes, as they only need their geometric primitive and their associated properties with that. So if I mean, I'm pretty sure you guys have heard of JPEG and PNG. So JPEG and PNG are very good examples of raster images, while PDF is very good vector images. SVGs also are very good examples of vector images. So let's talk about basic pixel representation and different color models. So so primarily, we are familiar with three, color models. One being the black and white, the other being grayscale, and another being the RGB. Which these three happen to be the most widely used, color models that the general population are familiar with. There are also other color models which I will be covering later on. So to start, we'll start off with black and white. So black and white. So when I talk about pixel representation, I'll be talking about rasters and not vectors because we'll be talking about individual pixels and not the geometric primitives. So with black and white, what essentially it means is that each pixel can only take either the value of black or the value of white. So in terms of binary, we represent that as 0 and 1, right? So black is represented as 0 and white is represented as 1. So since the pixels can only take two values, we kind of all or, it's also commonly known, black and white images are commonly known as binary images or 1-bit images. Now let's move on to grayscale. So with the help of grayscale, you can actually add a bit more depth to the images. So now if you take a look at the presentation, you can see the difference between the black and white and the grayscale. So you're able to differentiate that there are different colors on the screen, but you really can't tell what each color is. So what exactly grayscale images are is that, remember how I said pixels either take 0 or 1 in black and white, right? But in grayscale, we have 0 to 255, which is 256 values in total, where 255 is 255 is white and 0 is going to be black. And everything in between is the different intensities of gray. Now, this helps us add more pop to the image and gives more clarity on, different depths in the image, right? So since we have 255, 0 to 255, which is essentially 8 bits, we call grayscale images as monochrome images or 8-bit images. And the third is the most popular that we obviously use everywhere, which is the RGB color model. Now, RGB stands for red, green, and blue. And in RGB, each pixel takes a tuple of, a tuple. So essentially, the tuple has three values. First for red, the second for green, and the third for blue. And each value of red, green, and blue can vary anywhere from 0 to 255. Again, where 0 is black and 255 is, if it's red, it's red, and if it's green, and B is blue. All right. So RGB is also known as true color images, and since you have three 8-bit values that needs to be taken, we call it a 24-bit image. Now let's talk about another very basic part of image, which is image resolution. Now image resolution essentially refers to the number of pixels in an image, and it's often represented as width x height, and higher Resolutions mean more number of pixels, which also means that the picture is more clearer to look at than lower pixels. But that also means that will need more processing power than necessary to handle these kinds of images. All right, now that we're done with the image fundamentals, let's move on to what image acquisition is. So image acquisition in a way is essentially just ways for you to procure images. So when we talk about different applications of computer vision, there's the medical industry, there's the like Ravin talked about the medical industry, there's the autonomous vehicles industry, etc. So most of the time, people think that it's just using a camera, but there are other ways as well. Like in medical industry, we can use X-rays as a form of input, or MRI scans, CT scans as well. And there's also a different type of camera other than the conventional ones that we use, which are known as stereo cameras, which are basically where it's a camera that kind of simulates how our eyes work, and that's basically by placing two cameras in close proximity to each other and kind of overlapping both the images. So it kind of gives us the depth perception that regular cameras don't, the mono cameras don't get. So now that we understood what image acquisition is, we've understood what the basics of image fundamentals are. We'll move on to starting with the processing of the images. So we'll start with enhancing the images. Now, why do we need to enhance images? So without enhancing images, when you try to train your model to predict something, or try to detect something on a picture, it's going to be hard for the model itself, because there's a lot of disturbance in the image. So the accuracy of the prediction is going to be really low. Now, to prevent that, what we do is we try to enhance the images in different ways. So the most basic way to enhance an image is by brightness and contrast adjustment. So what does that mean? This essentially means that you're increasing or decreasing the overall brightness or the contrast of an image to improve its visual appearances. Now, where does this come into play? So let's say you have, in a data set, you have pictures that are from different times of the day, right? So early in the morning, it's going to be not so sunny, so the pictures are going to lack brightness, and towards the afternoon the pictures are going to keep increasing in brightness, and then you come to the evening, and then when you come back to the night, it's going to become dark again. Now, when trying to process overly bright or overly dark images is going to be a hassle. So what we try to do is we try to try to play with the brightness and the contrast for to get like on the right level, so that the model gets trained quicker and more accurately. And then there's another type of image enhancement, which is called noise reduction. So noise reduction essentially is like a way for us to remove noise. Now, what does exactly noise mean? So noise is the unnecessary black dots, or sometimes you might have dust particles in the pictures, or those uh, what exactly do you call this? When you kind of try, when like I talked about rasters, when you zoom in, you kind of get pixelated images. So sometimes you get pixelated images, and those pixelated images end up having a lot of noise. So we try to use the method called noise reduction to kind of make the picture look better and easier for processing. And then we have sharpening, which is basically increasing the contrast around the edges. So mostly in computer vision terms, we call it to be a contour. So what a contour essentially is the surface or the outline of the object that we want, which is our target object, right? So now when you try to sharpen the object, we're going to increase the contrast. So by increasing the contrast, what happens is it's going to look more sharp and more, easy to identify. Like look at the picture on the slide right now. So you can see that initially the picture looks very blurry, but after all the image enhancement is done, it looks very sharp, and you can kind of, say that okay, there is a cameraman and it's a black and white, it's a grayscale image, and he's holding a camera, wearing a black suit, etc. Right? So that's what we try to get. So after that, we have different other other enhancement techniques, but they're kind of technical. So I'll just talk about it like in brief. So we have histogram equalization. or medium filtering, bilateral filtering, etc. So these are ways for us to enhance the images. So let's kind of go deeper into what different ways we can enhance images. So image filtering. So like I said, we talked about the noise in an image, right? So when noise comes into play, it's really hard. So in the picture that's on the screen, you can see that there's a lot of white dots, and that's kind of annoying to look at. Over the period of time, when you try to train the model itself, the model is going to think that okay, the noise is also part of the object, and it's going to kind of lower the accuracy later on. So what we're trying to do is we're trying to eliminate the noise, and filtering is a very nice technique in image processing that lets you remove the noise. So you basically try to apply a lot of mathematical function to each pixel individually and change its value based on the neighboring pixels. And so let's talk about different image filtering techniques. So the first would be median filtering, like I said before. Um, Medium filtering, essentially what it means is that you're replacing the pixel values with the median values of its neighboring pixels. So essentially what you're trying to do is you take pixels, you try to find the median values of all the pixels around it and replace it with that value, right? So now how is that going to benefit us? So like you find the defective pixel and you try to make it better by normalizing it with the other values that are around it, and it's going to improve a lot by reducing the noise, and it's also great at removing outliers. Let's talk about Gaussian filtering. Again, Gaussian filtering and median filtering are similar, but instead of using the median values, we're trying to apply a weighted average to each pixel, depending on if they are pixels that we need or if we don't need them. And then we try to, blur them, or blur the image or smoothen the image with those weighted average values. And then there's bilateral filter, which is basically similar to Gaussian filtering in a way, but the way the weighted average is decided is by spatial distance and color distance. And this kind of filtering is essentially used to preserve the edges while smoothening an image. So when smoothening an image, things tend to happen where the edge also gets smoothed. So it's kind of hard to identify the contour of an object. To prevent that, we also use bilateral filtering. And then we have edge detection filters, which basically, try to detect the edge of the object based on intensity or color. We'll talk a bit more about edge detection later. And we have Laplacian filter, which is basically applying a Laplacian operator to an image to enhance its edges or details. Now, like I said, we'll talk about edge detection now. So edge detection is a very fundamental operation in image processing, and it involves identifying the boundaries of the object, which, like I said, it's also called a contour. And edges can be defined as sudden changes in pixel intensity or color, or other factors like shadows and reflections, etc. So edges essentially, now let's see the man's face, right? We're trying to detect what the edges are. Now you see that, I mean, like look at the top left picture. That's like the regular picture. Now look at the top right picture. So that's basically all the edges that we found with his face, right? So you can see that we got a basic outline of the face, locations where there are possible other edges like the hair or the eyebrows, the contour of the nose, the mouth, chin, etc. Right? So this kind of helps us to put in perspective that okay, so this is the face and these are the edges, and it becomes easy for us to process simpler images. Like when you have a bunch of lines and you're like, okay, these lines contribute to a face, so this is going to be a face. So it helps us in detecting things faster. Now we have a bunch of detecting edge detection methods. We'll talk about them now. So we've got the Sobel operator. Basically, the Sobel operator is again all of this. Since we talked about filtering earlier, all of these are essentially filtering techniques to detect edges. So Sobel operator is a filter that uses a kernel to calculate the gradient of an image. Um, Gradient of the image intensity in the x and y directions. Now, Essentially, what you're trying to do is see, you find the gradient, and when there's a sudden change with the gradient, you're like, okay, so this is an edge because there's a sudden change, and you make that mark that as an edge. So that's a serval operator was. And then we have canny edge detection, which is basically applying a series of filters, not a single filter, to an image to identify potential edges. And then you apply hysteresis thresholding, which is a method of thresholding, to connect the edges into continuous contours. And the final is the Laplacian of Gaussian. So this is a filter that involves an image with a Laplacian operator. So after first applying a Gaussian blur, we apply this filter, and then you can kind of find out the edge at different scales. Now, edge detection kind of has a lot of application in terms of computer vision, and the most primary ones are obviously object detection. So, yes, essentially, edges can be used to identify the boundaries of objects in images. Like I said, the face can be detected with edges being in certain shapes, and it becomes efficient for us to process them that way. So, object detection and tracking becomes easier. We also have image segmentation and feature extraction. So I'll talk about image segmentation next. But before that, I'll try to, explain what image segmentation is essentially. So edges can be used to separate foreground and background, right? And the separation of foreground and background is essentially what image segmentation is. Now, I'll talk about that a little later, but before that, let me finish off the applications of edge detection. So we have feature extraction as well. Now, edges can be used as features for machine learning algorithms. And, since features are a very integral part of training machine learning algorithms, we use feature extraction to extract the features and train the machine learning algorithms. So, you can later on use the models to classify or recognize images. And not a lot of people are familiar with edge detection and its importance, but overall, it's a very critical component of many image processing and computer vision applications. And yeah, to get started with computer vision, I think edge detection would be a great way to, understand how computers recognize and detect objects. So next we have image segmentation. Now, image segmentation, like I said, essentially is a way for us to separate the foreground and the background. Why is that important? Now, it is kind of in a way essential for us to understand that, okay, this is the object that we're targeting, right? This is the object that we want to recognize. So to kind of take that only that object from the rest of the image, we're trying to segment it into two. So it's like we're getting the foreground, which is the object of our interest, and the background, which we do not need necessarily. So we kind of use different methods to perform image segmentation. Yeah. So we have thresholding, which basically involves setting a threshold value for pixel intensities, and then you binarize the image. So binarizing in the sense you assign a foreground or a background for it. And it's a very common image segmentation method. It's also like to understand advanced image segmentation techniques. Thresholding is a very integral part. And we have it's not a very well-known segmentation technique, but watershed segmentation basically is a technique that treats image as a topographic surface. So if you've learned this in geography, you probably seen topographic maps, right? That give you two dimension. It's basically a two-dimensional map that gives you places where the peaks of the mountains are, or where it's, or the depth of the ocean is through topographic means, right? So using curves and the way different curves are drawn, you kind of get an idea. Okay, this place is higher than the other places. Similarly, the watershed segmentation uses a technique that treats the image as a topographic surface, and then it identifies basins or watersheds that correspond to objects in the image and kind of segments it into two. All right. So let's talk about object detection. So a lot of people have, you know, a kind of a confusion between what exactly image recognition and object detection is. So I kind of try to solve that for you guys. So object detection is a subset of image recognition that involves not only identifying objects in an image, but also locating their position within the image. This is the Google definition that I came across. So basically what it essentially means is that uh, so similar to how a machine learning by itself is a subset of AI. So it's probably not a good comparison, but yeah. So when I try to do image recognition, object detection happens first, and then you go for image recognition. So the way that works is that you try to identify locations of the object in an image, position the different objects that are there in the image, and then you proceed for image recognition. So typically how this works is that, so the thing is we'll be having a demo session later where we'll be demonstrating how exactly this works. But for now, you have to bear with me because I'll be doing the theoretical side. So this is the so typically you basically draw a box around the object that you want to detect, and kind of get the coordinates of the object that is being detected, and then you use the coordinates to further work with it. And the main difference between the image recognition and object detection is basically that image recognition focuses on identifying objects within the image, while object detection goes one step further by also locating objects within the image, right? As in, so image recognition is like, okay, this is a picture of a dog, but object detection is like, okay, this is the picture of a dog where the dog is at this coordinate, right? So that's what that exactly, I hope I kind of cleared it for you guys. If not, you'll probably understand it in the demo session later on. Well, we'll finish off with the last image processing technique, which is morphological operations. So morphological operations are essentially a set of image processing techniques that are used to analyze and manipulate the shape and structure of objects in an image. So let's take the original image right there. So it's a image that has the word test in it. Now, we're kind of going to perform different morphological operations on test. So we'll start off with my bad. So we'll start off with dilation. So what exactly dilation means is that you're trying to kind of uh, basically along the contour of the object that you're detecting, you're going to increase the thickness of the object by adding extra pixels along the contour. So dilation just kind of is a way to increase the size, and you know we have erosion, which is almost the opposite of what dilation does. And then we have thickening and thinning, which is basically adding pixels to the boundary of a foreground object until it's 1 pixel thick. And you know, yeah, I keep changing the slides for some reason. All right, so we have, like I said, dilation and erosion, and then we have internal and external boundaries, which basically kind of helps you figure out how the internal structure and the external structure of the object is. So internal boundary gives you the inside internally how the object kind of is. So okay, to put it in a better perspective, if you can see the bottom right picture, it says skeletonizations happen, right? So what skeletonization essentially means is that you're trying to keep the basic structure of the object while also trying to make it as small as possible. So just to get the basic topography. So internal boundary basically gives you the basic, topography of the object, and external boundary gives you the external contour of the object. And then we have thinning and thickening, which is basically, well, as the name suggests, thins the object or makes the object look more thicker. Now, so a very good example I can show you guys right now is the fingerprint biometrics that we've been using. So, fingerprint biometrics have been playing a huge role in terms of biometric authentications. So, everybody's phone has a fingerprint sensor at the moment. We have a lot of, biometric sensors in, when you go for work or when you're punching out and stuff like that, right? So, when you get the image of a fingerprint, you're going to have a lot of noises. You can see the white dots on screen, right? So those are what noise exactly is. And you kind of have uh, the fingerprint isn't exactly accurately taken. So what we're trying to do is, like I said, we talked about different morphological processing and segmentation techniques. So we're going to use that, and we're trying to remove the noise and make the ridges of the finger look more clearer. That way, it's we can kind of make it easier for the computer to authorize users. All right. So with that, we are done with the image processing fundamentals and different image processing techniques.
Just a minute, guys. All right. So now let's get into the topic called machine learning in computer vision. So machine learning plays a crucial role. We already know that, basically in computer vision as well. So like machine learning in computer vision is a field of study that focuses on enabling machines to interpret and understand visual information around the world. Okay, so computer vision applications includes object detection, image segmentation, facial analysis, and then recognition as well, and many other applications. So in computer vision, machine learning algorithms are used to enable the computers to learn from large amount of visual data, such as images, videos, and make predictions or decisions based on that data. So these algorithms can identify patterns, and relations that are, very very difficult to or impossible for humans to analyze and detect. Okay, and then these machine like these ML algorithms, use this information to classify and recognize and segment visual content. For example, we can like in the screen, in the left image, if we are opening a camera app in our mobile phone, okay, it starts to detect our face, right? It detects like this, it just detects the face, but it doesn't actually recognize our face, like this is Raven, this is Rohit. It's not recognizing the people, it's just detecting that, oh yeah, here's a face, and then yeah, here a person is there, and in the left side there's a person is there. It's detecting like that. But actual recognition system comes in Facebooks, Instagram, those kind of application like social medias. Okay, you can able to see that it tags the people, like as I shown in the right image. So it's showing that it is detecting the face as well, and it is recognizing the face, and it's telling the name as well, like Mark Zuckerberg. So this is how machine learning, like in the left image, there is no machine learning algorithm. It's just, computer vision algorithm which detects face. But in the right image, we can able to see that it detects the face as well as it recognizes the face and it gives out the name. So here the machine learning takes place. So this is how machine learning is implemented in computer vision. And now, before getting started with the live demonstration, I would like to, show the packages and libraries which are used for computer vision. Okay, so here I have, used four packages. The first one is the left side, the orange one is called PyTorch. The right side, it's called TensorFlow, and the bottom left one is YOLO, which is, you only look once. That is the name of the algorithm, YOLO. And then the bottom right is OpenCV. Okay, let me first explain about OpenCV because it is the fundamental package for computer vision. Okay, so OpenCV stands for Open Source Computer Vision Library. It is a popular open source computation library that provides, a range of tools and algorithms for image and video processing. It also has many functions to, for image manipulation, and then feature detection, object recognition, and so on. Okay, this OpenCV package can be used in wide range of applications, including robotics, augmented reality, and then surveillance systems. Okay, so next one is YOLO. Okay, as I already told you, YOLO is you only look once. Okay, so it is also an object detection algorithm, but the main thing is it uses a single neural network to detect objects in an image. Okay, so basically this the difference between the OpenCV and YOLO is that the YOLO algorithm is very fast and then very accurate, and it can able to detect objects in real time video as well, video streams as well. Okay, so this YOLO can be used in wide range of applications, including self-driving cars like Tesla cars, surveillance systems, and robotics. Wherever there is live stream or video, and you want to recognize faster you have to perform faster like image recognition, then you can make use of YOLO because it is very good at it. And then the last two, which is the PyTorch and TensorFlow, these two are the most popular used deep learning frameworks. Okay, that they are also used in computer vision as well. They allow the they allow the developers to easily build, train, and then deploy neural networks. Okay, deep learning neural networks and architectures for a wide range of tasks, which includes image classification, and then object detection, and then segmentation. And both frameworks offers range of pre-trained models. Okay, for example, I'm telling ResNets and Inception that can be fine-tuned for specific task. Okay, and then you can use those models to like building your own customized model as well. Okay, so these are all the use of these packages and libraries. So moving on to the next slide, which is the best softwares for computer vision. Okay, so I have mentioned three softwares here, which is PyCharm, VS Code, and Collab. Okay, like just let me know, guys, like which of these is your favorite. Like my personal favorite is VS Code, and then what is your favorite software? Like you can use that for anything, like for coding as well. I personally use VS Code for everything, for deep learning, for machine learning, for computer vision, for coding, and then for my digital assignments and other stuffs. So my personal favorite software is VS Code. What is your favorite? Okay, Epitome is telling Collab. Any other answers, guys? Rohit Jindal is also telling Collab. Nice, you guys are good users of Collab, I guess. Right. So we will, I will briefly explain the uses of these softwares. Okay. Let's start with PyCharm first. Okay. So PyCharm is a software which has these, you can use PyCharm for computer vision, and then these are all the advantages of using PyCharm here. So in PyCharm, first advantage is debugging and testing. Okay, so this PyCharm provides an excellent debugger actually. Okay, that allows you to debug your code line by line, and then you can set breakpoints, and then you can view the variables as well. So next one is code completion and navigation. Okay, like if you are working on a very large data set, then it makes this feature makes it even more easy. Like it makes even more easy because it has integration with popular libraries as well. Okay, like PyCharm provides integration with popular CV libraries such as OpenCV, TensorFlow, those kind of things. It will be integrated automatically in PyCharm. And then fourth one is you can easily customize the PyCharm as well. Okay, it is highly customizable. You can configure to your needs. Okay, and then the fifth one is the most important one, which is community support. PyCharm has a big community which is very active, which has many active number of users. And if you're having any queries, you can just go and clarify with them. You can share your knowledge. You can also contribute plugins and then provide support to PyCharm as well. So the next one is VS Code. My favorite advantage of this VS Code is it's lightweight. Like VS Code is so light than PyCharm. Okay, which makes it even more faster and more responsive. Okay, this is actually very important for computer vision projects. Okay, because you will be handling with a lot of data sets and then complex algorithms. Since it is lightweight, it will be very easy for you to get the response easily. And the next one is the customization. As I already told you, like VS Code is even more customizable than PyCharm. Okay, so like you can like it has lot of extensions that you can download and you can customize it actually. Okay, and it also has the support of debugging and testing as well. It is cross platform support. It has cross platform support, like it has support in Windows, Mac OS, Linux. You can use VS Code wherever you want, and it also has a very good community support. You can reach out there if you're having any queries. And then the last one is Google Colab. Google Colab is an amazing cloud solution where you can code in Google, like in online mode as well. Okay, so in online mode. So the first advantage is it is free and easy to use. Google Colab, there is no need of installation and setup and all. You need just a Google account to start your coding. Okay, and it is also very good for computer vision projects. The second one is Google. It's cloud computing, right? So it has high performance computing powers. Okay, Google Colab, it will be giving access to you with high performance computers, which includes GPU, TPU. Like it makes the deep learning and then the computer vision process even more faster. Okay, so the third advantage is integration with Google services. Okay, you will be like Google Colab integrates you with other Google services like Google Drive, Google Cloud Storage. Okay, these kind of features, it will be integrated with the Google Colab. You can it makes us easy to store those data set and then the saved Python notebooks in your Google Colab, like in your Google Drive, and you can easily import it to Google Colab and you can start working on it. And then the fourth one is you can collaborate actually. Like you can just share the Google Colab link to your friends and they can collaborate with the notebook as well. Okay. And they can also start working on the same notebook. And then the fifth advantage is you need not to install any libraries or you need not to install any packages as well, because all the packages are pre-installed in Google Colab. Okay. So it is you're ready to start your coding with it. And the last, you know, advantage is, but it's not the least, but I'm telling, Jupyter Notebook support. Okay, Google Colab supports Jupyter Notebook, which is an interactive environment for writing and running Python codes. Okay, so these are all the advantages of using Google Colab. Now it's time for live demonstration. So let me share my screen there. Just a minute.
Just a second, guys. Ravin will be back and we will start the live demonstration. Yeah, 2 minutes.
Just a minute, guys. Yes, this is the first live demonstration. Okay, this is the face detection program. Basically, we are going to detect the face as well as eyes from the camera. Okay, so here, like the code looks little intimidating, but I will make it even more clear so that the code will be very easy for you. So I have written it in Python. Okay, so actually computer vision, like this package has many, it has support in C++ as well, but Python is easy. So, and it has vast applications. So I have written the code in Python. Okay, so the first line is import CV2, which means you are importing the package. Okay, so the second, like the next two lines shows that it is called phase cascade. Okay, so we are using a function called cv2.cascade classifier. So this cascade classifier will load the cascade for the phase. You guys might be thinking, what is a cascade? Okay, so cascade is nothing but Haar cascade. It's basically Haar cascade. Haar cascades are type of algorithms that are used for object detection in computer vision. Okay, so it just works by analyzing the image to specific features such as lines, edges, and corners that are associated with the object of interest. Okay, so it has all the data about face, basically, in layman terms, something like. Okay, and then this, the next line is I cascade, and again we are loading the har cascade of I into this I cascade variable. Okay, so har cascade is nothing but it has all the features of ice, okay, which is loaded in this variable called I cascade using the function cascade classifier from OpenCV. Now I have written a function here which is called detect. This detect function has two parameters, which is gray, and then the next one is frame. We are handling, like we will be handling with grayscale images, because in computer vision you'll be handling mostly with grayscale images, as it has only one channel. Okay, which makes it even more computationally efficient, and you can make the process even more faster. So that's why we are handling the computer vision with grayscale images. And then the frame is nothing but the original input. Okay, original input from the camera. So this line is nothing but face cascade. Like from the face cascade we are using a function called multiscale, detect multiscale. Okay, this feature has three parameters. Okay, so which is the grayscale input, and then scale factor, and then the neighbor zone. Okay, so this scale factor neighbor zone, I got the best result with the numbers called 1.3 and 5, so I am sticking on it. Basically this starts to detect the faces, okay, from the in the grayscale input, basically. Okay, so now after detecting the faces, we have to mark, like we have to put that face in the box, right, so that we can see actually the algorithm is detecting the face. So for that we are going to draw a beautiful triangle here. Okay, for that I'm just opening the like the for loop, in which I have four parameters. Okay, so for x, y, w, and h. X and y are the coordinates, w and h are the width and height in the faces. Okay, so like for drawing the rectangle, we have a beautiful function called rectangle in the open source package itself. So you can just put the original frame, because we are not going to draw the face on the grayscale image, like draw the rectangle on the grayscale image. We are going to draw directly on the original image as well, original image itself. Okay, and then we are drawing the we are just adding the dimensions to it, and then here is the color of it. Okay, this color is in BGR format, so blue, green, and red. The first parameter is blue, second parameter is green, and then last parameter is red, so BGR. Okay, so I have written 255. 255 means the color channels, right? So 0 means it is like 255 means the actual color it is. Okay, so BGR, in BGR color 255 is nothing but blue color, so the rectangle will be in blue color, which detects the face. And then this is the thickness of the rectangle. I'm keeping it as 2. Okay, and this is ROI gray. Okay, ROI gray, ROI means region of interest. Okay, so we are cropping, like for this is for ice, I'm making for ice basically. Okay, so this ROI gray, I'm just cropping out the gray, I'm just cropping out the gray face, so that we can start working to detect the eyes from the face. Okay, and then this ROI color is nothing but the same, like the same face in color format, the original face in the color format. Okay, now we are using the same function as we have used in the face cascade dot detect multiscale. Okay, which is I cascade dot detect multiscale of here, instead of grayscale we are using ROI gray, which is nothing but the gray face. Okay, we are giving as input, and then for me these numbers worked well, so I'm sticking on it. Okay, so again for x2, y2, w2, and h2 in ice, the same thing which I'm just repeating that over here again. Okay, so cv2, again we are drawing the rectangle, but for this time it is for ice. Okay, so cv2 dot rectangle, we are using the color face, color, okay, color image of the face, and then we are drawing the dimensions of the rectangle. And then to differentiate, I'm using, for this is BGR, right? So BGR, so I'm using red color. Getting it? And then the thickness of the eyes, like the thickness of the rectangle which is covering the eye, which is 2. Again I'm using the same number. Okay, and then we are returning the original frame actually. Cool. So this is how the detect function works. So you will be getting the like you will be getting the input from the camera. It starts to detect your face with blue color rectangle, and it starts to detect your eyes as well with red color rectangle. This is how it works. Okay, so at last we have some codes here. I'll just tell you what it is. So to get the input from the camera, we will be using CV2 dot video capture of zero. Okay, this is a function which is used to start your webcam. Okay, and this zero means it is your integrated webcam. Okay, so if you are having some external webcam, you can use it as one, and if you're having more than one means you can use two, and so on. Okay, so now I'm going to get the frame. Frame is nothing but the image from the webcam. Okay, video from the webcam. So from video capture dot read. Read means it starts to record your video. Okay, and then gray equals to, like, we need to convert that into grayscale image, right? So it will be converted to grayscale image like this. CV2 dot CVT color, like convert color. Okay, we are passing the frame, and then to convert it into image, we will be using this function. Okay, like this thing, cv2 dot color bgr to gray, which converts bgr image to grayscale image. Okay, so now we are going to use detect function, which we have already. This is the function which we wrote here. Okay, so in which we are passing the gray image, and then we are passing the frame, original frame. Now this is called cv2 dot imshow. Imshow means image show from the open cv library. I'm naming the window as footage, and then I'm just showing the canvas in the sense the output image. I'm just displaying that. And these codes is for if I click the button q, the window destroys. The window will be destroyed. Okay, so just for quitting from the output. So now I will demonstrate how it works. Okay, like I'm just getting some error because my camera is in use here, right? Wait, I'll just turn off my camera so that it works. Just a minute, guys.
Alright, guys. So Raveen is facing a little small issue. So essentially, what's happening is that since right, so essentially, what's happening is that since his application requires his camera to be running, and we are currently using our camera to present on YouTube Live right now, his application isn't able to access the camera, so he's trying to figure something out. So if you can wait for just a couple of minutes, he will come back. All right. All right. So meanwhile, everybody's attending the session right now. If you guys have any questions at all that you'd like to ask me or Ramin, just put that up in the comment section, and I'll try to answer them like right now. And if I'm not able to answer them, I'll try to give you a resource that you can look forward to. Okay. So just quickly type in your questions in the comment section. That way I'll know what your doubts are. All right, Rohit. So primarily, there's a lot of courses that you can find online. I kind of learned it from this course in Udemy that let me just try to find I forgot what the course's name was, but yeah, you can try to find courses on Udemy or Coursera, whichever is comfortable for you. Try to learn the basics of image processing and try to understand the basic machine learning algorithms, and then you can kind of work on going to the more advanced neural networks with computer vision theories. So yeah, but yeah, if you really want to, I mean, I think the best source for learning computer vision would be the documentation and I mean, yeah, OpenCV's documentation. OpenCV has decent documentation, I would say. So you can look that up as well. And there's a lot of YouTubers that have been putting up computer vision related projects as well. And use GitHub as well. GitHub is a great way for you to, look at other projects and try to understand how they worked with, they approach different problems. And the last I would say, try to work on Kaggle a bit. So Kaggle, it's not just for computer vision. I would say if anybody that's trying to learn, that's getting started with data science or um, I mean, machine learning at all, you guys should really check out Kaggle. It is a great platform for you to learn and access different data sets. All right. Did I first learn about machine learning and then hopped on deep learning? All right. So personally, I started with the very basics of machine learning. So with like linear regression, that's like the basic. You start with that, and then you keep moving on until you reach different neural networks. So initially, the first time you start with machine learning, go to deep learning. And then the first time I came across computer vision in deep learning was when I worked with this particular neural network called CNN. Okay, so CNN is essentially a pattern detection. It's used for pattern detection. So it's widely used for uh, you know computer vision purposes. So it's like that. So you have to. I mean, it's recommended that you start learning from the very basics of machine learning so that it becomes easier for you to work on more advanced concepts. But I think in terms of image processing that I talked about, you don't need any, machine learning fundamentals, but image processing is a separate topic in itself. So image processing, if you want to learn, you can go with that. But if you want to, work with neural networks, I would suggest you start learning the basics of machine learning and then move to neural networks. All right. Any other question, guys? Okay, so for now, I'll let Raveen take over now, and we'll have one more Q&A session later on. All right.
Hello, am I audible?
Yeah, yeah.
Okay, cool. So, like as Rohit explained, okay, like the StreamYard is using my, webcam, and I couldn't able to, like, the program which I wrote couldn't able to access the webcam. Okay, and I don't have any other dedicated webcam as well. So that's the main problem. Anyways, I have taken these screenshots. Okay, screenshots of how the code works. Okay, so now you can able to see the screen, I guess. So as I told you, it starts to detect my eyes in red color rectangle, like it's rectangles, and then the blue color rectangle shows that it is the face, like it's detecting the face. So this is how the algorithm which I showed you works. Okay, so that's the basic one second. So this is the basic code in computer vision for face detection. Okay, so we have detected using eye cascades, eyes and hair cascades. Okay, so the next demonstration is, anyways, the next demonstration also won't work because this my webcam stopped working. Okay, so anyways, I have taken the screenshots for the next code, like the next code as well. Now I will just share my screen, and then I will explain how the next code works. Okay, the next one is hand recognition system. Okay, basically you will be like, I'll be showing my signs, like my hands gestures to the webcam, and it recognizes like which gesture I'm showing. Like if I'm showing a rock, it recognizes that it is a rock. Paper means it recognizes as a paper. Okay, now I will just share my screen now. Share the code now. Yes, hope the VS Code window is visible. All right. So here I have written four files. Okay. This is basically to detect whether the given gesture is a stone or paper or a scissor or a thumbs up. Okay. For these four gestures, I have written the code. Okay. This has integration of machine learning in it. So I have written four codes. This is the main code for running. Okay. And the next one is to detect hands. Okay, detect our hands, and then making the points on it. Okay, this is the code here. And then the next one is the ML model which I have used, and the last one is real-time data collector. Okay, so first I will start with the real-time data collector. It is nothing but, if I, like it's first, it is used to scan your hands. Okay, basically it is used to scan your hands, and then it makes a data set, okay, for the machine learning to predict what gesture you are showing. Okay, so I have shown four signs here, which is thumbs up, say, scissors, paper, and then rock. Okay, for these four gestures, it will start to scan your hand, and then it will collect data, and it will be stored in hands.csv file. Okay, so the next one is the ML model. I'll come back to that thing later. Now in this hand tracker, which is used to detect our hands, basically. Okay, for detecting our hands, I have used, there we have used cascades, basically. Okay, hair cascades for face and eyes. But here I have used MediaPipe, okay, which is an open source package from Google. Okay, so open source package from Google. Basically, it has many solutions in which I'm using the hand solution. Okay, that's what I have used, like mp.solutions.hands. So which is usually base like works for detecting hands. Okay, so this function discover hand is to detect the hand in the frame. Okay, and then it starts to draw the landmarks on it. Okay, this function basically works like that. And then the next one is def location. This location, this function is used to locate the points. I'll be showing that in the presentation. Okay, it's used to locate the point in the hand. Okay, so these two functions are in this thing, and this is main function, which is to test whether the code is working or not. Okay, so these two functions are important for tracking the hand. Now we will be coming to the main code. Like before coming to the main code, in the machine learning, like the ML model which I have used is support vector machine. Okay, in which I am using a classification model. Okay, so classification model is that you can basically classify whether it is a thumb or a scissor or a paper or a rock. Okay, instead of finding the values. Okay, so classification model works like that. So in the main code, we will be using the concept, like if like I will show the image. Okay, yeah, like during the like when I start to present the PPT, I will show you how it works. Okay, so if I start to show my hands to the camera, it will start to detect that whether it is a paper or a scissor or a rock. Okay, now I will just shift to the presentation for the live thing. Yeah, my screen is visible now. Yes. So see, the look like these are all the landmarks basically. Okay, I have marked, like if you count these things, okay, these points, there are totally 21 points. So let's assume that the like just take my pinky finger. Okay, the bottommost point and the topmost point, let's take these 2 points as the reference. Okay, so if the bottommost point, like if the topmost point is higher than the bottommost point in terms of y coordinates, then the finger is open. If it is going less means then the finger is closed. Okay, so based on this thing, I have written that in the in the main file. I have written that, okay, if this is for opening and closing of the finger. Okay, if that works, like the machine learning model will start to learn from the data which we have scanned basically. Okay, it starts to see whether the finger is closed or not. If the finger is closed, then, and like with the pattern, like it starts to recognize the pattern. And if the particular pattern, like if all the fingers are closed, then it is a rock. If all the fingers are open, then it is a paper. So basically it works on this concept only. Okay, so here in this case, all the fingers are open, so it is a paper. So it learns like that, and it recognizes the pattern as well. So here only the thumb finger is open and remaining all fingers are closed, so it's a thumbs up. So it recognized it well, right? So this is how the thumbs up works, like the model recognizes it. And then here all the fingers are closed, so it is a rock. Okay, and then here only the two fingers, that to the index finger and the middle finger, these two fingers are open and remaining all three fingers are closed, so it is scissors. So this is how the model works. Rohit, please take part, like take the session now.
Uh, hey guys, I am back. So we have a question from Rohit again, asking why we're using CNN instead of normal neural networks. So Ravin, do you want to take up that question?
Yeah, which question? Rohit Jindal.
So the comments, yeah, Rohit Chandra.
Like we can implement all this using normal neural network layers with a couple of hidden layers. But you are using, but where you specify? Okay, basically it's not CNN, it's normal thing only. Okay, so here we didn't use any neural networks here. I have just used a machine learning model called support vector classifier. Okay, so CNN is nothing but it will read from the image and then it will predict, like it is a classification model which learns from the image and then it starts to classify it. Okay, so here in this second live demonstration, there is no need of using CNN algorithms. You can just use normal machine learning model, or you can use normal neural network as well, like which is artificial neural networks. Cool. Hope I cleared your question.
All right, guys. Any other questions that you guys want to ask? You can just put them in the chat box and we'll get you like immediately. I'll give you like 5 minutes of time and then we'll move on with the question after that. Okay. So just try to ask any questions that you have related to what happened in the session and we'll be happy to get back to you. I can't see any questions coming in. So yeah, I think we'll continue it, right? Um, all right. So, all right. So for anybody that wants to, you know, get started with machine learning or computer vision in general, you can visit our Notion resource link. So this has, resources with respect to any, in terms of if you want to get started with machine learning or computer vision in general. We have all the resources up there. So I'll just leave it here for a minute so you guys can, just take a picture or, access the link. All right, guys. So the three QR codes you can see on screen. The first one is Ravin's. So if you want to look into all the projects that that were discussed in this particular session, you can go check out Ravin's GitHub, and there's all of the repositories over there. And IEEE VIT's Velour's GitHub is also on screen. So if you guys want to contribute to any of the projects that currently we're working on, so all of these are open source projects, you can gain a lot of experience from them. So if you want to contribute to them, then you can go ahead and look into our, I know IEEE VIT Velour's, organizations GitHub page as well. We have a bunch of projects going on, and the last is mine. So again, I do have a bunch of open projects that are going on. So you can, you please feel free to, go check at them and contribute to them if you want to. And we also have so IEEE VIT Vellore also has a wonderful Techloop community. So the link to the community's Discord will be put in the YouTube chat, and we'll also put in the attendance form in the chat box for everybody to access and put in your attendance later on. All right. So I can just say that I think somebody asked a question, right? how much time will it take for me to get basic knowledge of machine learning if I start now? So honestly, I think it depends on what pace you're going at and how much time you dedicate towards learning machine learning because it's different for everybody, right? Everybody has their own pace at what they learn. Some people are very fast learners, some people are slow learners. So don't worry about how much time it's going to take for you. As long as you're consistent with what you're doing, you should be able to see results. All right. So if there's any other questions that you guys want to ask, just put them in the chat box. And yeah.
Any other question, guys?
All right, so I don't see any more questions on the chat box, so I guess everybody's asked their questions, and I think we can end our session with right? It was nice taking the session for you guys. We had a very fun experience doing this for you guys. So yeah, stay tuned. Check our Instagram page for more updates on upcoming sessions if we do conduct them, and make sure you join our tech loop as well. We will be having a lot of fun discussions in the Techloop Discord as well. So yeah, cheers. Have a great day. Okay.
Thank you, guys.